Two, three, four, our fourth lecture on moments. And moments are going to be really important. We're going to continue seeing this, having to use moments, and actually we'll expand on that use of moments as we go pretty much the entire semester. The moment is really important. Just want to check, is everybody feeling the moment? Is everybody feeling that? Okay, so we're all feeling the moment here together, and today we're going to talk about moment of a couple. And so first we need to be able to identify and define a couple, and so we'll talk about that. The net force for a couple, that'll key us into some interesting properties for the moment of a couple. And then we can be given basically these three different ways. We can be given couple forces, asked to calculate the moment of one or more couple forces in 2 and 3 dimensions. So we can see both 2 and 3 dimensions. Or given couple moments, calculate the resultant couple moment. So this one, we start with moments, and we're asked to find the resultant moment. The first one, we were asked to find the result moment given forces. So we started with forces. And then the other one is we could go the opposite direction. So given a couple moment, go back and calculate the force to produce that resultant couple moment. And then also we have coordinate direction angles for couple moments. We talked about coordinate direction angles for a moment last time in the moment about an axis stuff that we did. So our homework, we're going to see 2D problems like this. A couple just means that there's equal and opposite forces. So you see this first one right here, we've got 2 forces. They're going in equal and opposite directions. And we're going to write all this stuff down. The next one, we have 2 sets of equal and opposite. And then the next homework problem, we have 3 sets of equal and opposite forces. And so you're going to see that in your homework. And then you're going to see, given the magnitude of a couple moment, we're in 3 dimensions now. Given the magnitude of that couple moment, go backwards and find F. And so we're given where F is located. We have this 3-dimensional system going on here. And so we'll talk about how we can solve problems like that. And then this one is actually when we're given, instead of being given the forces, we're given the couple moment. And actually we've really seen couple moments before. We just didn't call them a couple moment. We called it just a moment. And it's because there's no net force on this system right here, right? There's no forces applied to this. There's just moments that are applied along some axis of rotation. So when we have moments that are just applied along some axis, that means it's a couple moment. Okay, and we're going to write all this stuff down and talk about it. And so the first thing here, just for our visual learners, right, a couple moment just means that we have 2 equal and opposite forces. We're going to learn how to calculate those here today. So actually, let's just jump right onto the paper here, and let's write down some of these things that we've talked about. So moment of a couple. And when we have a moment of a couple, it means that we have 2 equal and opposite forces. That's really a moment. When we have couples, there means they're equal and opposite forces. The concept is exactly the same as before. And what I mean by that is that we can find the moment is equal to F times D, or if we want to find a moment vector, it's R cross F. So there really is, there's really not a big difference here. It's just that we have 2 equal and opposite forces, and actually it makes it easier. It actually makes it easier for us to calculate the moment when we have 2 equal and opposite forces. And so let's look at, what if we started a lot of our discussions this moment with showing like videos of me holding a board or something like that. And so let's take a board here. Let's say we had a board, and let's apply 2 equal and opposite forces to that. Let's say over here, I apply a force, we can call this FA equal to 10 newtons. And then let's apply a force over here. Let's say we've got a force over here of FC. We'll call this one FC is also equal to 10 newtons. So we're applied at those two different points there. And let's put some, let's call this point A right here. I'm going to make point B actually right in the middle of that beam. This is point C where we said FC was located. And then actually let me make another point over here just off of our board, and I'm going to call this point D right there. Now I want to go through and let's just look at how this is the same. The concept is the same as before. So if I take the moment about point A and I just say, okay, let me take the moment about point A right here. We need some dimensions on there, don't we? If we're going to do that, we need to know what some distances are. So this distance from here, from A to B, that's 1 meter. The distance from B to C, that's another 1 meter. And the distance from C to D, that's another 1 meter right there. So we just have all 1 meter distances on this thing. And so if we're finding the moment about point A, remember in 2D, we can always say that the counterclockwise rotation is going to be positive, right? And so if I take the moment about point A, first FA, and we can think about our physical object here. There's this FA pulling up right there, but we're taking the moment about point A. Does FA cause a moment about point A? And let me ask somebody from the front row here, Katie Longcore, what's the force, what's the moment about point A from the force at point A? From just the force at point A.
Can the force cause a moment about point A?
Exactly, it can't, right? It's because the line of action is going right through point A. So if I'm like holding a ruler and I'm pulling up this way, there's no, if I'm holding a ruler right here and I'm pulling up, there's no tendency for it to rotate, right? Because that line of action goes right through there. So FA is really, we could take FA, but it's going to be times 0 meters. So, right, it doesn't cause a moment, absolutely. Okay, now how about FC? Now FC over here, is that going to cause a moment about point A? Yes, it would, right? Because we have some perpendicular distance. We've got FC pushing down over here, and it's going to cause a rotation going clockwise. So it's going to be a negative, and the perpendicular distance to it is going to be 2 meters. And so when we plug all this in, we've got 10 newtons times 2 meters. We're going to end up with a minus 20 Newton meters, aren't we? For that one right there. Now, what if I go to, let's take the moment about point C now. I'm going to skip over to point C. That's on the line of action of the other equal and opposite force. In this case, wouldn't it be FC times 0 meters, because FC is going right through point C, but then we'd have FA. So about point C, right? FA would be causing, again, a clockwise rotation. So a minus FA times 2 meters is equal to minus 20 Newton meters. So we found exactly the same thing for taking moments about A and C. What if we went over to point B? Okay, is it still going to be the same? So if we take moments about point B, we're going to have a minus FA times 1 meter. And because FA is causing, if we look at, it's causing a clockwise rotation. And then FC is also going to cause a clockwise rotation. So it would be a minus FC times 1 meter. So we still end up with negative 20 Newton meters. And then what if we did this about point D? What if we said, well, what about the moment about point D? That's got to be different, right? We've got to find a different value than negative 20 Newton meters. Let's see, FC. So we're looking at rotations about point D. So FC, that's going to cause a counterclockwise. So there's a positive. Okay, stuff is changing here. So we'd have a positive FC times 1 meter. And then FA over here would still cause a negative or clockwise rotation. So it's going to be a minus FA now times 3 meters. So, hey, wait a second. Actually, this is still negative 20 Newton meters. So when we have a couple moment, when we have two equal and opposite forces, the moment about any point is the same. It's basically, it always has the same magnitude and direction. I mentioned earlier that couple moments actually make things easier. And the reason is because we can pick a point that involves less math. If we pick a point on the line of action of one of those, then we have less math that we need to do. So it's easier when we take the moment about a point on the line of action of either force, right? It doesn't matter which one, but if I take the moment about the line of action of FA, or if I take the moment about the line of action of FC, I have less math to do. Now, if we're just doing the 2D problem, not a big deal, right? Not a big deal if we took the moment about, A or B, which isn't, B is not on the line of action. And so we had two terms technically that, that we had to do in our calculation. But imagine now if this was a cross product. Would you rather do one cross product, or would you want to do two cross products? I think I would rather just do one cross product so that I don't have as much math to do, right? Okay, so what this is, a moment of a couple, this is referred to as a free vector. This free vector means that basically we're free to take the moment anywhere and we're going to get the same thing. Okay, that's everything we just wrote down there in green and purple. That's what makes that thing a free vector. And then the other thing that let's write down is that the net force on the system applied to the system is equal to 0, isn't it? So it's all pure rotation. So that's what so these are all the properties when we have a moment of a couple. We know it's just pure rotation. There's no net force applied to it, that it's a free vector. So no matter where we take the moment, we're going to get exactly the same. We're going to get exactly the same value. So how can we apply these concepts to a problem with more than one set of couples? Let's go and let's take our board here and let's apply two sets of equal and opposite forces to this board. We'll stick with how about we stick with an FA? And I think our FA was going up. I'll just make this FA right here. It doesn't matter when we're doing moment stuff. It doesn't matter if I show these as pushing or pulling forces. Notice if I go back to my original problem, I showed FA as kind of looks like it's pulling on point A. FC is pushing on point A. That doesn't really change anything in terms of our calculations or what we're doing. Now notice I changed FA is going both, is in both examples, in both pictures here. Like on the left picture, I have FA pulling up, in my right picture over here, I have FA pushing up. Doesn't change the math at all. It really doesn't really change anything for us at this point in the semester. So FA going up there, that's all that really matters if it's going up or down. And then we'll make, actually I'm going to call this one FD because we're going to add some points here. So FD, and we'll keep that, we'll keep these at 10 newtons. So that's, FD is 10 newtons, FA is equal to 10 newtons right over here. And then we're going to add a couple more couples. So how about one right here? We'll do this FB, and that's going to be at an angle of 60 degrees. So we're going to make this FB, and that's going to be 20 newtons. And then we're going to have one that's equal and opposite to that. This is FC, and that's also equal to 20 newtons. And then for our geometry here, let's see, we're going to have some distances here, like horizontally, these distances in between each point there is 1 meter. So we're going to make this 1 meter, 1 meter, and 1 meter. And then we do need the height of this one for this problem, and that's going to be 0.5 meters for the height. And these forces are at a 60-degree angle and a 60-degree angle on both of those. Okay, so that's what we're given. We're asked to find now the resultant couple moment. When we are dealing with anytime we see equal and opposite forces, we know it doesn't matter what point we find the moment at. It could be point A, it could be point B, it could be point C, or it could be point D. It really doesn't matter where we take the moment at. And actually, you're going to see in the problem statement, they're not going to tell you, oh, what's the moment about point A? Before, when we didn't have equal and opposite forces, we were always told, oh, take the moment about point A, or take the moment about point B. Now that we don't have equal and opposite forces, it doesn't matter because they're always going to be the same. Okay, so for our solution here, we can find MR, and I'm just going to specify it as, let me see here. So MR, the resultant couple moment, is going to be a combination of the 10 newtons and the 20 newtons. And let's treat them separately, right? Because they're each kind of separate, equal, and opposite forces. So for like, if I wanted to deal with the 10 newtons, so I'm ignoring the 20 newtons for now, I'm just dealing with the 10 newtons, which 2 points would make it really easy for me to take the moment about? Like, where should I take the moment about for, if I'm dealing with the 10 newtons? Kaylee LaRue, what 2 points could I take them about and make the math easier?
I'm thinking A and D.
Absolutely, right? They're on the line of action of A is on the line of action of the 10 newton, D is on the line of action of the 10 newton. And it doesn't really matter which one. Let me take the moment about point A. So if I'm taking the moment about point A, I'm only paying attention to the 10 newtons. I've got 10 newton over here. It's going to cause a clockwise rotation. So it's going to be a minus 10 newton times 3 meters. So that right there, that was really what I did, is I took the moment about A for only the 10 newton forces. I'm done with the 10 newton forces, right? I don't have to go, do I have to go and calculate them at D also? And add that? No, right? Because I am done with the 10, no matter, if I move to D, what would I get? I would get negative 30 newton meters again, wouldn't I? Okay, so I only have to do it once. So now we're done with the 10 newtons. Let's move on to the 20 newtons. Now, when we have forces at, well, first, actually, before we get to the angle stuff, the fact that we have a force and an angle, the 2 points that we want to take the moment at for this one would be either B or C, right? Because B is on the line of action and C is on the line of action. It doesn't matter which one of those I pick. Either one, if C is easier, or if B is easier, pick that one for you. So for the 20 newtons, it's going to be, we have an angle here. Easiest way for us to handle angles is to break those up into components, right? And so we're going to have a Y component and also an X component. Now, I talked earlier about the FA, when I first drew it, it was pulling. Now when I drew it, it's pushing, and how that doesn't matter. Now, one thing that does matter though is when we draw components of a force, make sure that all the arrows are touching at the same spot. Notice that the tip of all my arrows is touching, right? So the tip of all arrows are touching. Right, so make sure that that does happen. Don't draw your components, what I'm talking about doing, and I'm going to erase this. What I'm talking about doing is like, what if I drew my component up here and right there, I just did that in orange, right? Where all my tails are touching. Well, but I don't know where that is, right? I don't know where my tail is. I know where the tip is. The tip of that is specifically at point B, isn't it? Okay, so we draw the components there. And so what I'm going to do is I'm going to take moments about point C then. And so if we take moments about point C, we're going to have the FBX component, right? And so FBX, the horizontal component, is going to the left. That's going to cause a counterclockwise, so it's going to be positive. And then it's going to be multiplied times which distance? If FBX, and let me label FBX on the picture here, that's FBX is the horizontal one. What distance do I multiply it by in that case there? Spencer, Needler, what do you think? FBX times what distance?
Is it the 0.5 meters?
Yes, absolutely, right, because that's the perpendicular, that's the distance that's perpendicular to the line of action of X and goes back to point C. So yes, so 0.5 meters, thank you. So FBX times 0.5 meters right there, it's positive because about point C, it's causing a counterclockwise rotation. So I did the X component. How about the Y component? FBY, and that one is going to be times 1 meter. And is that going to be negative or positive? That's going to be positive as well. It's about point C. It's causing a rotation that's counterclockwise. This is us taking the moment about C for only the 20 Newton forces. And we're done though. That's all the stuff that we need in our equation. So MR, let's expand this out, minus 10 newtons times 3 meters plus our FBX, let's see, that would be 20 times the cosine of 60 times 0.5, and then plus 20 times the sine of 60 times 1 meter, and we're going to find a negative 30, and we get a negative 7.68 Newton meters. And that negative, what is that telling us? It tells us that the moment goes clockwise. Right, so if we got a positive, it would tell us that it goes counterclockwise because we set positive, right? For all of our stuff here, we said that this direction, that counterclockwise, was positive. Okay, and I see I have a question here. Why is fx multiplied by 0.5? Fx is multiplied by 0.5. I always leave my phone on. That's like the first time that my phone has gone off in class, right? That tells you how often people bug me. Okay, so anyways, so where were we? Okay, so point 5, right? So remember, we're taking moment about point C. So right here, we're taking the moment about point C because we said we're going to pick a point on the line of action. FBX is up here. FBX is causing a rotation about point C that is positive, and the distance to that line of action of the X component, we're only looking at the X component, that distance is that 0.5 right there. Okay. So isn't it, it really is exactly the same as before, right? It's just moment times the distance, and so we can just pick a spot that's easier for us, can't we? In order to make the math a little bit easier. What about this problem? Here, let me copy it up to here. So if we still are writing stuff down, we can see this as well. So this will be now, how about we do a 3D example? Okay, and in this example here, we have, and we're going to draw this picture, but just to get us familiar with this before we start, we've got a 35K here and a negative 35K there. So this, we're in 3D. They're giving, the K is the vector, the component of the vector, right? So that's a Z component because we see our Z axis is here. And then we also have a negative 50I and a positive 50I. And so 3D is the same way as in 2D, where let's pick a point on the line of action of those couples. And so we could pick, you know, for the 50I, we could pick its line of action is here for that 50I. So we can pick any point on that line of action, or we can pick any point on this line of action. That's right there, right? So any point on that line of action, and we'll draw a picture of this in a second. And then for the 35K, we can pick any point on this line of action and any point on this line of action. And so let's go ahead and let's draw our given information. And so in this problem, they've got the Z-axis that's going straight up. They've got the X-axis. They've got the Y-axis kind of angled too. I'm going to do the Y-axis just straight off to the right. And then we've got the X-axis coming out of the page right there. Our pipe assembly goes along the X-axis. So just draw right along the X-axis right there. Notice that this line right here, this purple line that I'm drawing on the picture, is parallel to that Y-axis line right there. So actually maybe why don't we do like a dash line that's parallel to our Y-axis, and then our pipe assembly goes above that dash line, doesn't it? Kind of curls up and goes above that dash line right there. And then the last segment of the pipe here, that goes parallel to the X-axis, so we can just go parallel to the X-axis right there. Ooh, and let me see if I can I move this over so it's not hanging over my picture? Hey, look at that, pretty cool. Okay, so then let's draw our forces here. I'm gonna do them all in red. Let's see, right here, we've got a 35, that's not a 3K, how about a 35 K hat going up. Over here we've got a negative 35 K hat going down, so those are equal and opposite. Right here we've got a 50 I hat. Oh, that's a negative 50 I hat. And then over here we've got a positive 50 I hat right there. And they've labeled some of these points for us. I'm not going to draw any of the dimensions because what's actually easier is to list out the coordinates, right? So A, B, and point C here. And actually, I've already done that work for us. So like point A has coordinates here of 3, 50, 0, 0. So we can just consider this to be given to us. Point B has coordinates of 350 minus 346.4 and a 200. And then point C over here, I'm going to need more room than that for point C probably. Point C has coordinates of 600 minus 346.4 and a 200. And then point O has 0, 0, and 0. So again, using the coordinates is helpful for drawing pictures in 3D. Also is going to really be helpful for when we solve this problem, isn't it? And what we're asked to find for this one is the resultant moment vector, MR. And actually what I want to do is I don't want to work this whole problem. This problem is up on Canvas under the supplementary. If you want to look at the full solution, let's talk about let's set up our cross products, because we've already done the cross product. We should all be able to just, once we figure out our R, once we figure out our F, we should be able to do the cross product. And so if we want to do, if we want to find MR, remember we're going to pick a spot on the line of action of one of the forces. Why don't we start with the 50 I's? And so what 2 points could I use for the 50 I's? I could use either A or C, right? So what if I did the R from A to C? So if I did R from A to C, where am I taking the moment at? I have specified where I'm taking the moment at by saying I'm going from A to C. Anyone, where am I taking the moment at? At point A, right? Because wherever the position vector starts, that's where we're taking the moment. So RAC crossed and it ends at our force, right? So the position vector starts where we're taking the moment, it ends at our force. So that's going to be crossed with a negative 50I, because the negative 50I is at C. So actually that's the only cross product we need for the 50 I's. Both of them. It takes the positive and the negative into account. And then we also are going to need the cross product for the 35Ks. How about A to B crossed with then, again, actually I'm taking the moment about A, aren't I? So I'm still taking the moment about A, but I'm ending it at B, and that's going to be crossed with a positive 35K hat. So this would be that's one possible way to do it. I could also have done, I would have found exactly the same thing if I did, what if I did this? R from B to A crossed with a minus 35K hat plus R from C to A crossed with a plus 50 I hat. I'm going to get exactly the same thing. Or couldn't I take the moment about point O too? What if I took the moment over here about point O? I would have to do ROA cross minus 35K, ROA cross the 50I. ROB cross 35K, ROC cross a minus 50I. And I'd have 4 cross products. Now, would I want to do that? Probably not, right? Because I'm just doubling the amount of work, but we would get exactly the same. And so remember, the very first problem that we started with, we always got, no matter what point we took the moment at, right? With this very first one, whether we took it at A, B, C, or D, we always got exactly the same thing. So the moment at any point, it doesn't even have to be on the physical object. You could take it 1,000,000 miles out in space and we'd still get exactly the same thing. So pick the easier points though, right? When you're looking at all those homework problems, pick those easier points. Any questions? Okay, so that takes us through 2D and 3D when we're given forces and asked to find a moment. This also, we didn't do it specifically, but we would use this same technique if we were given a resultant moment vector and asked to find the forces to produce that. But we have one more instance that we need to look at. And that one more instance is when we have something like this, where we are just given straight away a couple moment. And so in this case, now somewhere down along this pipe here, there are 2 equal and opposite forces that are applied to this. In order to get this to do that, we would have like these 2 equal and opposite forces applied, but they don't give us that. They say, no, we're not going to give you that part. We're just going to start you with this. Now remember, if their net force is 0, these are free vectors, meaning the moment that they create is the same regardless of where they're applied. And so this picture down here, what it's showing us is, notice that even though this moment is up here and this moment is down here, what it's showing us is that our MR is just the vector sum of those 2's, and we can move them, right? They move M2 down a little bit and they move M1 up a little bit because they are free vectors, okay? So now I just wanted to, to iterate that for this example. So let's take a look at this example now. And we're asked to determine the resultant couple moment. When we have these pure moments, when they don't give us the forces, when they get right into the moment straight away, we're basically doing the same thing. We're going to treat them exactly the same as if they were force vectors. And we were looking for the resultant force vectors instead of the resultant moment vector. So we have a y-axis, we have a z-axis, and then they have their x-axis coming out of the board here. And what they tell us is that we have a moment vector. This is M2. I'm going to draw it with 2 arrows. M2 is equal to 30 pound-feet. And they're showing us that it's in the xy plane. This is just like the planar projections we saw in force vectors. Isn't this line right here that I just did in red on the image? That is parallel to the x-axis, right? Let's draw a dashed line parallel to the x-axis. And then there's a line back here that's parallel to the y-axis. So parallel to the y, and it's going to intersect. I guess I need to extend this, my x, going back into the page here. And so we can show this is parallel to the y. Now, doesn't that look like it's in the xy plane? A little bit more than at least before. It looks definitely like it's in the xy plane over here in this actual picture. And so this is 30 degrees right there. And then they have for this other one, it looks like I need the negative y-axis on here as well. They show this other one where the line of action of this is kind of going like this. And so I'm going to draw it. I guess I can draw that one right there. M1 is 40 pound-feet. And I'll put 2 arrows on there. And we can include that shaft on there if we want to. We can show, okay, well, this is where the shaft is. Here's a piece of that shaft right there, and then there's another shaft over here on this side. But I don't think we need to draw all those gears or anything, right? And then they're showing us where M1 and where M1 is located using some dashed lines here. So that first dashed line is going straight down. I have another line that goes back to the origin, and then I have another line that's parallel to the x-axis. And they tell us that this angle right here is 15 degrees, and this angle right here is 20 degrees. This is actually your homework problem too. For this topic. So, all we need to do is, if this is our given information, and we're asked to find the resultant moment vector, MR. And this one, they might actually ask us for the alpha, beta, gamma too, I think. Alpha, beta, and gamma. So, all we have to do is the same thing as if these were force vectors. Like if this was an F1 instead of an M1, wouldn't we just need to find the X, Y, and Z components based on those planar projections? And we know what direction it's pointing in. It's got up down and to the right. Let's look at M2. Let's formulate M2 because that one is only in two planes. M2 is going to be equal to, let's see, in the I direction. So let's start with the I component. Wouldn't M2 have a negative I component? Because isn't M pointing in the negative X direction? So it'd be a negative I. And then wouldn't it be 30 times what? The sine or the cosine of 30 degrees? So it's at 30 degrees, but is it sine or cosine of that 30 degrees? How about Ben Eidler?
Sorry, do you mind repeating that one more time?
Sine or cosine for the I component?
Oh, sorry, for which one?
For the I component, for the X component.
Okay, it should be cosine, right? Oh, for that one, it would be sine.
Sine, yes, thank you. Awesome, nice job. Sine of 30 times I. That's going to give us the I component. And we had to pick that it was negative. Remember, with planar projections, we do have to pick the signs. We have to figure out what those signs need to be. And then for the J component, it's positive, right? It's pointing in towards the positive Y direction. And so that's going to be a positive 30 times now the cosine of 30 degrees. And that's our J, and then plus a 0 K hat. Now, this problem is also in the supplementary problems that are up on Canvas. Basically, to finish this, we need to figure out M1. So we're going to have to do our planar projections. We have two right triangles in this case. Same process as we did with forces. I'll just put ... here, right? You need to find the I, the J, and the K components. And then to find MR, all we have to do is add M1 plus M2. Good question. The supplementary problems, if you go to the additional resources or something at the bottom of the homepage, I think is where they're called, like, yeah, additional resources or additional links or something like that at the bottom of the homepage, and then you'll see the supplementary example, a link to the page with all the supplementary example problems. Okay, so we add M1 and M2 together, and then how about alpha, beta, gamma? Well, we can find cosine alpha as the MRX divided by the magnitude of MR, and then beta and gamma, same kind of way there. So thank you all.